Hello, everyone. Thank you all for joining us today. Our panel today is held in honor of World Engineering Day for Sustainable Development, an event which was held by UNESCO for the first time last year, and which celebrates engineers and their role in helping communities achieve the United Nations' 17 Sustainable Development Goals. Our session today focuses on arguably one of the most important or most essential of these goals, which is Sustainable Development Goal number 6, clean water and sanitation. The targets of SDG 6 include ensuring safe and affordable drinking water, access to safe and affordable drinking water for all, improving water quality, protecting water-related ecosystems, and improving wastewater treatment, recycling, and reuse rates. This goal has never been more important. According to the UN, 2.2 billion people still lack safely managed drinking water. Many countries around the world are consistently registering very high water stress. In 2018, 60% of 172 countries reported that they were unlikely to meet the targets of SDG 6 by 2030. And so the challenges are enormous, and engineers can play a very, very significant role in resolving these issues. And that's the topic of our discussion today. So joining us to talk about these issues today are professionals with extensive experience in helping communities get sustainable and long-term value from their water resources. Our first speaker is going to be Mr. Karim Azam. Karim is a groundwater engineer who specializes in groundwater assessment and modeling. Karim, thank you for joining us.
Thank you, Haya. Hi, everyone.
We're also joined today by Scott Smith. Scott is the head of sustainability and the Building Physics Group and Daryl's London office, and he has over 30 years of experience in water resource management. Scott, it's an honor to have you today.
Thank you, Haya, and hello, everyone.
Joining us as well from Pune, India, Naveen Garg is a senior drainage and infrastructure engineer with 14 years of international experience. In the field of drainage and infrastructure design consultancy, he holds a Master of Technology degree in Water Resource Engineering. Naveen, thank you for joining us.
Thank you, Aya, for inviting me to this important event. Thank you.
And finally, we have Mr. Marcus Philippopoulos. He is a senior infrastructure and treatment engineer who holds advanced degrees in hydraulics, hydrology, public health, and environmental engineering.
Thank you, Haya. Hello to everyone.
Hello. Thank you all for joining this panel. So Karim, we're starting with you today. Karim, beginning with you. So the first target under SDG 6 is providing universal access to safe and affordable drinking water. And one of the most critical resources for this goal is groundwater. So tell us a bit about this resource. Why is it so significant, and what are the challenges associated with managing it?
Thank you, Haya. Yes, indeed. As you probably already know that the 70% of the surface of the Earth is covered with water. However, most of that water is salt water in the ocean, so that's not usable. In fact, only 2.5% of all water on Earth is fresh water. And from that, about 70% is also, again, frozen in glaciers and ice caps, so it's not immediately usable for communities. This leaves us with groundwater, which constitutes about 30% of all fresh water on Earth, which might not sound like a lot, but it actually serves as the primary freshwater source for upwards of 2 billion people. So that's why for us as engineers, it's very important to appreciate our role in managing this resource sustainably. And for that, there are two main challenges. The first main challenge relates to the quantity of the water. So the idea is to extract enough water to meet the required demands while not depleting these resources and maintaining them as renewable resources. And the other aspect is in terms of quality, where you don't want any contaminants or pollutants from the surface to deteriorate these resources. So to illustrate that, this is an exceptionally important problem for us as engineers, particularly in urban areas. For example, if you have in the condition where you have excess groundwater abstraction, you might have a dangerous phenomenon that is known as land subsidence. So that's essentially when the surface of the soil, surface of the earth settles due to removing too much water from under it. That can lead to flooding. That can obviously lead to devastating consequences on any underground structures, on the infrastructure, and that can cost up to hundreds of millions of dollars. On the other hand, some other cities, particularly new cities, can have the opposite problem. In fact, instead of a fall in groundwater levels, you could have a rapid rise in groundwater levels. That is due to excessive recharge from the surface, which can be due to leakage from utilities, could be due from excessive infiltration from irrigation or landscaping at the surface, and in coastal communities, that could be due to the influence of seawater level rise. Obviously, again, in this situation, the shallow subsurface becomes saturated with water, and that can hurt or have a negative impact on any infrastructure located underground. So just to illustrate that, I'm just going to quickly talk about an example of a city located in the Gulf region. The images on the left show how quickly the city expanded over a period of 30 years. And in recent years, citizens started seeing damage to the roads, damage to the infrastructure, and that was all due to the shallow groundwater table, which rose as a result of all this new infiltration that's happening. Even though at the time of construction, it wasn't necessarily very shallow, but this recharge had an impact on the infrastructure. So our objective here was to design a system to control the water and maintain it at an acceptable level, while at the same time maintaining the city services in operation. So in order for us as engineers to do this, to come up with the optimal solution, what we need most is data, and not just general data. What we need is local data, site-specific data that we can then import into a groundwater flow model or a numerical model. And this data is used to calibrate the model to basically mimic the actual conditions on site as they are, and then we can from that make projections. So as you can see, the slide shows just how complex the patterns are under the city, the groundwater patterns, and there's obvious mounding in certain areas. And that groundwater contour map can be turned into a map of depth to water, as we can see here. And from this map, you can see the red areas are areas that are identified as critical and that need extra attention in our design. So having identified these critical areas, our solution for this problem was to implement a subsurface drainage system. So that is essentially a network of perforated pipes that are placed under the roads and that collect the water and effectively lower the water table to acceptable levels, while not really disturbing what's happening at the surface. The next slide shows just quickly the results of this, of the simulation. After implementing the subsurface drainage system, as you can see, the critical residential areas have had their groundwater lowered. So having said all this, the question that remains is, what do we do with all this water? I mean, you might think that this water that is extracted from these systems is not significant or doesn't have good enough quality. However, in our experience, and we've come to believe that every drop of water that can be used should be used, particularly in cities that have high water demand. So the idea here to improve the sustainability of the city, the plan is for this water, which by the way was found to have good enough quality and had a large enough volume, that the idea is that it will be used for landscaping and other municipal uses across the city. So it was important to us to turn that problem into a benefit.
Excellent. So you protect the infrastructure and you also be able to reuse the water sustainably.
Yes, exactly.
Karim, another important aspect of SDG 6 is to make sure that communities have access to the drinking water resources that they need. You also mentioned that you were working in very dry regions, and this is very important in such areas because they suffer a lot from water stress. And sometimes to deliver water to such communities, you as an engineer need to try unconventional approaches. So when we began preparing for this panel, you mentioned one project in particular that was quite ambitious. Describe this project for us.
Yes, indeed. This project is what is known as an aquifer storage and recovery system, which, as the name implies, is a system for storing water essentially underground and then retrieving it whenever it is needed. So for this project, excess desalinated water from city operations was introduced in an aquifer that is located essentially in the middle of the desert, a few kilometers away from the city. And the idea or the challenge for us here was to design an optimum solution or an optimum operation scheme between infiltration and recovery in order to ensure that this water, the water that is introduced into the aquifer, is not lost into the depths of the aquifer, and at the same time, whenever you need it, you can retrieve it easily from these recovery wells that were also constructed in the aquifer and pumped directly back to the city. So again, here, what we needed the most to simulate this model and come up with the optimal solution was data, was local data. On the next slide, you can just see some of the examples of the data that was collected. We were lucky to have a lot of data for this project. Again, all of this data was introduced into a groundwater flow model. Especially the problem here was particularly complex because not only do you have to model the flow of water, but you also have to model the interaction between the fresh water that is introduced and the salt water that is already in the aquifer. So from the creation of this model, we can create a number of scenarios, of forecast scenarios that model that basically tell us what would happen under different recharge scenarios, different infiltration scenarios. Essentially, the images that are seen on the screen just to show a quick indication of how this freshwater lens that is introduced it evolves with time. So essentially, on the left, the higher the hydraulic head means the more water is introduced. And then in the image on the right, that shows the concentration. Concentration is represented by the blue water. So the more blue you have on the image, the more fresh water is present. And then that can allow us to design any mitigation measures as needed to maybe prevent the water from escaping too far into the aquifer or anything of the sort. So this was just one example of how us as engineers have a responsibility or have a big role in promoting the resilience of cities and promoting the sustainability of cities and their readiness in the face of emergencies. The optimum scenario that we came up with for this project allows the city to have a supply of up to 90 days of fresh water at a rate of 40 million gallons per day. So that's what was important for us to promote the sustainability of the cities, especially in these times where with climate change and many other factors, emergencies are becoming more and more common.
Thank you very much, Karim.
Thank you, Haya.
Okay. So as Karim has demonstrated, managing groundwater is essential in empowering communities to meet their water needs. But just as important is what happens on the surface. So our next speaker, Mr. Scott Smith, is an expert in water resource management, especially as related to water efficiency, water harvesting, and recycling and reuse technologies. Scott, you work on both small-scale projects, such as buildings, and you also work on master plans for entire cities and developments. And sometimes you work within very specific restrictions and regulations. So tell us about your experience.
Thank you, Haya. Yes, if you could go to the next slide, please. All projects need an understanding of the water and sewage and stormwater constraints for projects and sites in the Middle East and worldwide. In my opinion, the main engineering challenges that we face in terms of water and sanitation is to establish water budgets for our projects and master plans. That is potable water, gray water, treated sewage, effluent, and sewage. We need to understand these inputs and outflows to better create the design. The determination of the amount of available water from all sources coming into and out of the project boundaries is key to a good design. This ensures that the designers understand the water limitations and needs of the site and adjust their designs accordingly. This also assures that the water efficiency measures that we implement, like low flow toilets, water efficient fittings, water efficient irrigation, gray water systems, etc., that are put in place are justified and relevant to this design. Next slide. Looking closer at the urban site water constraints, potable water and sewage is usually provided by the municipality or the utility providers. The problems associated with obtaining the water and treating the sewage are for a kind of others to solve. But unfortunately, as cities mature and become more urbanized, more and more utility providers are imposing constraints and conditions in urban settings on how buildings and projects can connect into their services. In terms of stormwater constraints, which with climate change and the increased frequency of major storm events in the world, most sustainable urban drainage system solutions will not work based on the space constraints in the urban environment and practical issues associated with the site. There is usually no room for swells, wetland features, ponds, etc., with most site area covered in hardscape and impervious areas, which makes storm events and handling the rainwater more important. Therefore, for the determination of urban water budgets, this requires establishing design principles around how to connect into services, inputs and outputs, which lead to gray water and rainwater harvesting and stormwater management solutions. Next slide, Haya. If we look at a typical urban area where site constraints typically occur, new construction usually requires the demolition of existing buildings with the construction of a new building. Hit the next slide, please. If we take a look at this building, and next, and if we can remove it, and knowing that the sewage and associated rainwater run around the site, next, please. And I know that the connections of this site actually occurs in 2 points, as indicated in the purple areas. Next. And I know this is the case. Next, please. Because this is our new building, the Dar Group new headquarters in London at 150 Holborn, which is currently under construction. In established urban sites like 150 Holborn, water utilities set the typical size of water connections and meter constraints for the total amount of potable water that can be provided to the site. Sewage outflow needs to be established without exceeding the amount of sewage already connected from the existing building. For 150 Holborn, the utility company mandated that the stormwater peak outflow needs to be reduced below 50% of the expected 1 in 100 year storm event from the previous building that was on the site, if we're going to connect rainwater into their sewer system. In addition, the planning authority, which this building is under the control, required that the design of the building provide rainwater and grey water harvesting systems, and that 60% of the available credits in the UK Sustainable Certification, BREEAM, which is a requirement for planning, need to be achieved before construction takes place. So we had to show in our design that we would be meeting 60% of the water credits on the sustainable certification. The sustainability group in London, which I am a part of, have made great efforts to ensure that the water efficiency is at the heart of our new European headquarters building in London. We have established that and ensured that the constraints in terms of reduction in potable water consumption, sewage outflow, and stormwater attenuation imposed by the site and the local utility providers are met through a combined greywater rainwater harvesting system that works in combination with the building's stormwater attenuation system. Next slide. I would like to quickly explain the engineering solution that has been designed for this building that meets the requirements of both the utility company and the planning constraints. This is a very simple schematic of the greywater harvesting and attenuation system that is being constructed for 150 Holborn. And the reality that with multiple downpipes and different roof areas, it is more complex. So yeah, I will just be providing a very simplified explanation of what the real design will be. The main features of the system is a blue roof, rainwater diverter valve, the rainwater greywater harvesting system, and the rainwater attenuation tank in association with smart building technology. Next slide. In the UK, if the Met Office issues a flood warning or weather alert for the London area, the smart building technology detects this alert and will configure the building to be prepared for this event. This is done by opening the valves in the intake tank on the greywater rainwater harvesting system and the rainwater attenuation tank to ensure that they are both empty. Next slide. The rainwater diverter valve is then set to allow the rainwater to empty into the rainwater greywater harvesting tank. In the first instance, the blue roof is then allowed to fill up. The blue roof will capture the first 50 millimeters or 2 inches of rainwater, which then slowly drains the roof at an established rate at the gullies. If more rain falls that exceeds the 50 millimeter level over the time the roof is allowed to drain, this rainwater overflows into the rainwater downpipes and into the rainwater building's rainwater system. In turn, the rainwater and greywater harvesting tank is then filled. Next slide. Once the rainwater greywater harvesting tank reaches capacity, the rainwater diverter valve then switches to allow the rainwater to fill the rainwater attenuation tank. If the rain event exceeds all this capacity, it is then allowed to discharge into the sewer. This system is designed to store over 50% of the rainwater precipitating onto the site in a 100-year storm event based on the existing building that was on the site previously. Next slide. After the rainwater event occurs, the blue roof slowly drains away, then the rainwater attenuation tanks drain. The system is designed to release the rainwater over a period of hours, reducing the storm surge in the sewer and any possible damage to the municipal sewer system that this could have caused. Next slide, please. This building that is designed and installed into our new building has allowed the design aspects of the building to meet the highest sustainable certification standards of LEED, Platinum, and BREEAM Outstanding, which is the highest certification levels that we can achieve. This also allowed us to achieve all the water credits for both certification systems. So for LEED, we got 11 out of 11 credits, and for BREEAM, we got 9 out of the 9 water credits. Next slide. This same problem can apply to other urban areas of the world and the Middle East due to climate change impacts. Obviously, other cities besides London will have differing levels and complexities associated with water and sanitation, and may not need to utilize engineering solutions that we have put in place for 150 Holborn. I think Kareem's previous presentation explained different kind of design solutions for other urban areas. But these, for well-established and older cities, for instance, London, these are kind of the only options that we would have to employ. These urban images that are on the screen show the same possible site water constraints that could be a requirement now or in the future for each of these locations. And just to go quickly, the images are Beirut at the top left, Riyadh, Cairo, Amman, Pune. In the middle right is London, and at the bottom is Dubai, Doha, and Kuwait. So as you can see, all of these cities can and might have the same constraints that we face for our new London headquarters. Thank you.
Thank you, Scott. These are definitely issues that are becoming even more and more important with the climate change and all of these issues. Thank you very much for that.
You're welcome.
So our next speaker, Naveen. Hello, Naveen again. So Naveen also contributes extensively to Sustainable Development Goal targets 6.1 and 6.5, which are again to ensure universal access to drinking water and implement integrated water resource management at all levels. So Naveen, a question to you. What is integrated water management exactly, and what has been your experience with its major challenges?
Actually, integrated water resources management is a process which promotes the coordinated development and management of water, land, and related resources to maximize the resultant economic and social welfare in an equitable and sustainable manner. So this is based, the integrated water resources management is based on mainly three principles. First is social equity, and second is economic efficiency, and third is ecological sustainability. So social equity means ensuring equal access of water in adequate quantity and quality for all the users. And economic efficiency brings the greatest benefit to the greatest number of users possible within the available financial resources and water resources. So this requires that the most economical efficient option is selected. The economic value is not only about price, it should also consider current and future social and economical costs and benefits. So what is ecological sustainability? Ecological sustainability requires to avoid or limit land uses and developments that negatively impact our ecosystem. Haya, can you please go to the next slide? Yes. So what are the challenges we face in integrated water resources management, planning, and design? Mostly we face four challenges. The first one is unavailability of topographical information or the ground information. So this information is required to develop the understanding of contributing catchments in a particular region to estimate discharges. And the second is historical rainfall data. So this historical rainfall data is used to get information about rainfall pattern in the region and to estimate the water storage volume in the area. And the third one is existing groundwater levels. Generally, we don't get this information in developing countries. And if we can get this information, this provides us the condition of water exploitation, how much water has been exploited. And in case the water is at shallower depth, as it was mentioned by Karim, in urban cities, we need to know this information to design the concrete structures. And the fourth one is gauged river discharges. This information provides us the valuable information about historical flow rates of any river or catchment from a catchment. And also it provides relation of the flow rate with the catchment parameters such as runoff and rainfall. Can you please go to the next? So what are the solutions that can be adopted to overcome these challenges? So first challenge we had or we discussed was unavailability of topographical information. So in that case, we can explore SRTM data which is available. And what is SRTM data? SRTM data is a shuttle radar tropical mission data that provides digital elevation model of 30 meters spatial resolution, and it can be used in ArcGIS platform to prepare catchment and stream delineation of an area. It also provides contour levels. And the second challenge we discussed was absence of historical rainfall data. So this challenge can be overcome by using TRMM data, and the TRMM data is actually a satellite data, and the full form of TRMM is Tropical Rainfall Measuring Mission, and this provides short-term historical rainfall data from year 1998, and it also provides the rainfall data with reasonable accuracy, and it gives general idea to the engineer about the rainfall pattern in the area of interest. And the third challenge we discuss about existing groundwater level. So in absence of existing groundwater level information, what we can do, we can visit the site, try to find out the existing water wells, and we can measure the water levels in the water wells in order to get the information about the current condition of groundwater level. And the fourth challenge we discussed was about absence of gauged rainfall data, gauged flow data, river flow data, and this challenge can be overcome by using the combination of SRTM, which is topographical data, and TRMM, which is rainfall data. So if we use the combination of these two data, we can estimate the river discharge with the help of available discharge calculation methods such as SCS method or the rational method. Can you please go to the next? So actually you have to go back a bit. Yeah, this one, case study. So these solutions generally we adopt in the project where data is not available. And now I'm going to present to you a case study where all the previous mentioned solutions are adopted, whether it is use of SRTM data in absence of topographical information, or TRMM data for rainfall pattern or measurement of groundwater in existing wells. So this case study is from an African city where existing water supply source is only groundwater and it was overexploited. And in addition, the city has witnessed rapid urbanization since past 2 decades, and that also has aggravated the situation. So due to the depletion of groundwater table, farming in the region has been adversely impacted as the cost of water extraction has risen a lot. So even in some locations, the groundwater, the wells were running dry and there was no water anymore. So what happened after that? The city administration decided to improve the current water supply system in the city and selected DAR to propose a suitable solution that can serve 3 main purposes. What are these 3 main purposes? First is rehabilitation of water supply system. Second is replenish groundwater table. And third is to provide adequate irrigation water to the farmlands. So this case study is from an African city where what we are doing, we are proposing a dam, a multi-purpose dam to supply water via transmission line to the city in form of loops, and this dam shall discourage the water wells, the use of water wells for water supply and for irrigation, because as I said earlier, many farmers were exploiting or withdrawing water from the wells to irrigate the land. So this dam shall supply water to the city water supply system, as well as this dam shall supply water to the farmlands available at the downstream of the dam. So in addition to that, we also proposed a wastewater treatment plant at the end of city limit to treat the wastewater up to a suitable level for irrigation. And after treatment, this water shall be discharged into a stream from where all the farmlets at the downstream can use the water for irrigation. So this was a good example of integrated water resources management we developed, and I just wanted to share it with you. Now the question is whether such process can be implemented in other developing countries or not. So can you please go to the next slide? So in applicability in other developing countries, how we can apply it. So I believe nowadays the developing countries are finding themselves in a state where current water use practices are leading to water deficit and not able to cope up with the new challenges such as population growth, rapid urbanization, changes in rainfall pattern due to climate change, and increase in water demand in agriculture and industrial sector due to rapid growth. And this we are witnessing in India quite a lot nowadays. So all these aforementioned issues can be addressed by integrated water resources management process that can help developing countries to focus more on economic and social growth without compromising the sustainability of environment. Thank you.
Thank you very much, Naveen.
Thank you, Aya.
So we concluded with the note that integrated water management is one of the solutions for promoting sustainability. Our final speaker, Mr. Marcus Philippopolius, is one of DAR's leading water treatment engineers. Marcus, SDG 6, and just the talk from Naveen right now about integrated water management. SDG 6 recognizes the importance of water reuse, recycling, and water treatment. And in some areas, especially those that have low water resources, treated water can make an incredibly significant positive impact. So finally, I'll leave the floor to you to discuss water treatment and the different applications that it could have.
Thank you, Haya. It's an honor for me to be with you today. I'm going to talk to you about wastewater reuse in the Middle East. As you may know, Middle East faces an increased scarcity of water since it is one of the driest regions in the world. The problem becomes even bigger due to the fact that most groundwater aquifers contain brackish water. Therefore, there is a need for non-conventional water resources, such as seawater desalination, wastewater reuse, and rain harvesting. The use of large seawater desalination plants creates a new environmental problem, the increase in salinity of the Arabic Gulf, since the reject brine from the desalination plants, which is very high in salinity, is disposed back into the sea. Also, due to the region's hot climate, there is an increasing demand for water, make-up water for cooling towers. This demand can be satisfied from wastewater reuse. There are two types of wastewater reuse: grey water reuse and wastewater, or otherwise known black water reuse. We call it black water in order to distinguish from grey water. So what is grey water? Grey water can be defined as a low polluted stream of domestic wastewater collected from bathroom sinks, showers, bathtubs, and washing machines. Kitchen sinks and dishwashing machines are usually excluded from the grey water stream due to their high pollutant loads. So as seen from this figure, grey water can account for up to 44% of domestic water use. After treatment, grey water can be used for toilet flushing inside buildings, irrigation purposes, and as make-up water in cooling towers. Grey water treatment and reuse can reduce domestic water demand by at least 40%. Here we can see the expected grey water quality in comparison with black wastewater quality. Now I would like to give you an example of grey water treatment from a building in Dubai. The grey water treatment plant receives 170 cubic meters of grey water, and the plant is located in the basement of the building inside an area of 90 square meters. As we can see from the process flow diagram, the process includes flocculation, sedimentation, ultrafiltration membranes, known as UF membranes, and the treated water is stored in a balancing tank. From the balancing tank, it's pumped into the building's toilet flushing network and the irrigation network. The plant produces 150 cubic meters of grey water. The losses of 20 cubic meters per day are due to backwashing of the UF membranes and the waste sludge which is disposed. The treatment of grey water can, as we said, can be used for toilet flushing and irrigation purposes, and in this way we can reduce our freshwater demand by at least 40%. Now I would like to give you a second example from black wastewater reuse in Kuwait. The plant is expected to receive 600,000 cubic meters of raw wastewater at its final phase. The treatment includes, as we can see from the process flow diagram, screening, oil, grit and grease removal, primary sedimentation, biological treatment, filtration, and final disinfection. The biological treatment includes nitrogen and phosphorus removal, so that at periods of low irrigation demand, the treated wastewater can be safely disposed into the sea. The waste sludge is anaerobically digested so that we can produce heat and power from the biogas released from the process, which is the heat and power which is produced from the biogas is sufficient to run the digestion process on its own. Now, the digested sludge is further dewatered and mixed with wood chips to produce compost for agriculture. Therefore, we can see that this plant is a very good example of sustainability, since everything is reused, nothing is wasted or dumped. All the wastewater comes in, is treated and is used for irrigation, and the waste sludge is made into compost and used for agriculture. Now I would like to give you another example of wastewater, black water reuse for cooling tower use from Saudi Arabia. The plant receives 80,000 cubic meters of treated wastewater from a channel which leads to the sea. The treatment, as we can see from the process flow diagram, includes for filtration, chlorination, chemical pretreatment, ultrafiltration, reverse osmosis, and chemical post-treatment. The treatment is required to remove the excess salinity, the total dissolved solids, and spikes of nitrogen, and of course to disinfect the wastewater. The recovery from the RO system is estimated around 75%, and the overall plant recovery is around 70%. The reject brine from the process is discharged back into the treated wastewater channel leading to the sea. The reduction of TDS in cooling water helps to conserve even more water, since the cooling plant blowdown cycles are reduced. The plant produces 60,000 cubic meters of makeup water, which is used in the airport cooling plant. So in this way, we can save 60,000 cubic meters of fresh water. Now, as we can see from the examples given, different treatment processes have to be used depending on the final use of water. keeping in mind that the ultimate goal is to minimize the potable water demand through environmentally friendly, sustainable solutions. Thank you.
Thank you very much, Marcus. So we have about a few more minutes left. I'm going to open the stage for questions. If you have any questions for our, I've been receiving some questions already, but if you have any questions for our panelists, please feel free to ask them at the moment. So Karim, I received a question for you.
Yes, sure.
Yeah, it's about the groundwater project. What kind of data exactly do you require for the groundwater control and the aquifer project, and so what kind of data was required, and how do you create, what's the design process for the drainage system? I'll just get back to those slides.
Sure.
But please go ahead.
Yes, so hydrogeological systems or groundwater systems are very complex and very heterogeneous. So as I mentioned earlier, you do need site-specific data because no two systems are the same. So you need water levels, you need measurements of hydraulic conductivity measured through pumping tests. You can have a measure of concentration if the issue is fresh water versus salt water. So that's the more data that you have, the better it is. And as Naveen was talking about the importance of data as well, it's very important for us as engineers from different trades or different disciplines to share this data together, and then we can incorporate it and come up with an optimal solution. Or it's important to help each other. And then you also asked me about the process for design. So
Karim, can I ask you something?
Yes, of course.
There is another question, which is how do you know that your model is working? How do you know that? How do you confirm that this model works? Because you mentioned
so obviously
create a model for this, and how do you know that it actually represents the correct conditions?
Yes. So as I said, all this data when you create this groundwater flow model or groundwater mass transport model, you need to calibrate it based on all of this data that you collected. So actually what you see on the screen now, the graphs on the bottom left and bottom right give an indication of the accuracy of the model. So they compare for example, the graph on the right compares measured values versus simulated values. And then when these two curves match, then that means that your model has a high level of accuracy. And then you can use it to simulate scenarios, to integrate it into your design, or do whatever you need to do with it.
Perfect. So you test it against the data, you mean?
Yes, you do test it against the data, and then you use that in the designs. I think the next slide has, if you can switch to the next slide, please.
Oh, yes, sure. This one?
Or the one afterwards. Yes. Yeah, so all of this data basically comes down to this, comes down to software. Basically, the design for this subsurface drainage system was an iterative process between multiple types of software. On the left, you have basically network design with conventional software for network design, for wet utility network design. And on the right, you see how the invert levels and the layout of the pipes is introduced into the groundwater flow model, and the groundwater flow model gives you the flows that go into these pipes, and it shows you it gives you an indication of the impact of these drains after they are introduced. So here I think there's a very big opportunity for us as engineers to integrate, especially with all this new technology, this new software that comes up. There's a very big opportunity for us as engineers to combine all our knowledge together, be it knowing, having an understanding of the site constraints mentioned by Scott, or sharing our data mentioned by Naveen, or be it finding a reuse for wastewater instead of disposing of it in an improper way, as was mentioned by Marcos. So I think there's a very opportunity there looking ahead at the future.
Perfect. Thank you, Karim. We have one more question for you from Tony. He says, did you use the variable density flow model to simulate freshwater injection? So did you use a variable density flow model to simulate freshwater injection? I'm assuming that means that's for the...
Yes, I believe he's referring to the aquifer storage and recovery system.
Yes.
So obviously, yes, that would be on the next slide. Yes. So just an indication can be given on slide 16 if you want. It's
Yes,
just an indication of, as I said, so the freshwater here was introduced into a saline aquifer that basically acted as a container. So this model mentioned by Tony basically allows you to you import it into a finite element model, and it allows you to not, as I mentioned earlier, because saltwater and freshwater, there's a lot of intermixing, there's chemical processes that occur, and it's important to import all of these parameters from the tests that were done on site and from the data that was collected on site. Obviously, it is necessary to use it because you don't want to lose the water. You don't want the fresh water to just mix up with the salt water and then it's not usable anymore. You don't want it to go into the depth of the aquifer and be it not usable. Actually, there already is a huge loss of water, but this is more innovation is always on the move to come up with new ideas.
Excellent. Thank you, Karim. And there was one other part of Tony's question. He also asked, was the density of the existing groundwater mapped?
Yes, obviously it was mapped based on all of so for this model, as I said, luckily we had a lot of data that was collected over the years since the start of the construction of the project, upwards of 10 years ago or around 10 years ago. So we not only had the recovery wells that were installed near the 3 infiltration basins, but also we had data from the environmental agency of that country. We had to map that data, digitize it in GIS, combine all the data that we have from third-party wells, from additional wells located not only within the boundary of the model but also outside of it to basically interpolate determine the conditions of the model, determine its boundary condition, determine the stresses that are acting on it, and so on and so forth.
Thank you very much, Karim. I actually also have a question for Scott.
Yes.
You have you up here. The question we received was about smart technologies. You mentioned that smart technologies are what control the greywater system that you are the rainwater harvesting system. The question we got here was what other smart technologies are used for this process?
Yes, for 150 Holborn, we've created a smart technologies backbone for the building. And in terms of water, obviously there's a lot of metering that goes on. So we're able through the meters and the smart technology to understand where the water is flowing throughout the building. Obviously tank levels, when it's being discharged. Also, we have smart taps and fittings that is part of kind of the Internet of Things that allows us to understand and know what's going on in terms of water efficiency techniques and stuff. So in theory, our building will be quite at the forefront of the smart buildings technology system.
Okay, thank you very much, Scott. Okay, well, so we'll conclude our session here today. Thank you all very, very much for joining us. This was our first panel discussion for Sustainable Development Goal number 6. We're going to be hosting a couple of more sessions for the other panels. So we're going to be discussing SDG 7 later on and SDG 9. Once again, thank you very, very much, Scott. Thank you for being here with us today. Karim, thank you for your presentation. That was a lot of very, very helpful information. Naveen, thank you again for being here. I know it's late in Pune, so thank you for joining us from over there. And Marcus, of course, thank you for everything.
Thank you, Haya.
Thank you, Haya.